So we're going to talk about the last problems for this answer key, and I want to really focus on number 13 in large part because it's the one I want to focus on in terms of how I got all the things to happen the way that I did, because this type of problem is what caused a lot of questions when people were doing it in class. So you were given magnesium carbonate and you were given hydrogen phosphate um, as reactants. You were also given MgCO3 and aqueous and H3PO4 aqueous as reactants. So you had this as a reactant or set of reactants, and you had these as a set of reactants. You had to first predict the product. So I said identify both of the products by name. So I was looking for you to match up the words or the names over on the product side. So we have to remember the generic formula for a double replacement reaction, which is AX plus BY makes AY plus BX. And that means that if A and magnesium are together on the left side, A and magnesium have to be together on the right side. And X and carbonate on the left side, X carbonate on the right side. B and hydrogen on the left side, B and hydrogen on the right side, Y and phosphate on the left side, Y and phosphate on the right side. Okay, so that's the easy part of it. The next thing you have to do is then go ahead and match up the corresponding elemental symbols, right? So we had to identify that Mg on the left side is magnesium, so magnesium on the right side is also going to be Mg on the right side. So following that logic, phosphate on the left side is going to be phosphate on the right side, PO4 on the left side, which I believe that should probably be purple, so I should make that better. So PO4 on the left side is going to be phosphate and PO4 on the right side. Hydrogen carbonate on the left side is going to be CO3 on the left side. So carbonate on the right side is going to be CO3 on the right side. And lastly, hydrogen on the left side is going to be H on the left side, and hydrogen on the right side is going to be H on the right side as well. Another thing you had to do is identify the charges of the cation and the anion, the plus and the minuses. So we went through in the process of doing that. Up here, you should have done that. So this is just an application of that skill that we worked on above. So how do we do that? Well, I went to the periodic table and I located Mg. Magnesium is in the second column, so it's a +2. And I wrote that right here. I looked really hard for CO3 over here and I couldn't find it. So I found CO3 on the back side, which is carbonate, right here. And I see that it is a -2. So CO3 is a -2. Hydrogen, I went and found on the front side of my periodic table, right here in the first column, it's a +1, so it's a +1 here. And then phosphate, nowhere to be found on the front side, so I'm going to go to the back side, and when I look at the back side, I find phosphate right here, which is PO4 -3. So this is a -3 charge. So again, if your charges are +2, -2, +1, -3 on the left side, those same charges have to be present on the right side. So for example, magnesium is a +2 and PO4 was a -3, just like they were on the left side. Hydrogen is a +1 and CO3 is a -2, just like it was on the left side. So then you had to go through and like cross these things down or put them behind each other. So the 2 from magnesium went behind the phosphate right here, and we dropped its plus, and the 3 from phosphate went behind the magnesium right here, and we dropped its minus. At this point, I would have checked to see if the 3 and the 2 could be simplified. They cannot, so it's Mg3PO4 2. Here, for hydrogen carbonate, the +1 from hydrogen went behind carbonate and the -2, and we dropped the plus sign, and the -2 from carbonate went behind the hydrogen and dropped the minus sign, and that's how we ended up with H2CO3. The last thing that we had to do was identify which product was aqueous and which product was solid. So we're going to consult our solubility rules, which are these right here. So I'm going to look at this compound only, and I'm going to start with rule number 1. All compounds with group 1 metals like lithium, sodium, potassium, or Li, Na, and K are soluble. Neither of those are present, so I'm going to go to rule number 2. All nitrates, NO3, nope. Acetates, C2H3O2, nope. Chlorates, ClO3, nope, are soluble. So we're going to move on. Chlorides, Cl, not present. Br, bromides, not present. Iodides, I, not present. So we're going to move on. Sulfates, SO4, not present. So we're going to move on. All compounds with carbonate, CO3, chromate, CrO4, hydroxide, OH, phosphate, PO4. There it is. That's the thing we're looking for. So now we need to finish reading the rest of this rule. It says all compounds with carbonate, chromate, hydroxide, phosphate are insoluble. So that leads me to believe that this is going to be a solid, and it is a solid because of rule number 5. So now I need to focus on this product right here, okay, H2CO3. And again, I'm going to start with rule number 1. All compounds with group 1 metals, Li, nope, Na, nope, K, nope. Moving on to rule number 2. All nitrates, NO3, nope. Acetates, C2H3O2, nope. Chlorates, ClO3, nope. Moving on to rule number 3. All chlorides, Cl, nope. Bromides, Br, nope. Iodides, I, nope. Moving on to rule number 4. All sulfates, SO4, nope. Moving on to rule number 5. All compounds with carbonate, CO3, there it is. So now I have my carbonate, and that rule says all compounds with carbonates, chromates, hydroxides, phosphates, or sulfites are insoluble. And this is insoluble except if they're with group 1 metals or ammonium and hydroxide and barium hydroxide. So group 1 metals, this is where things get a little shaky, but the reality is that hydrogen oftentimes behaves as a group 1 metal. Also, oops, dang it, I did this again. Also, another way to look at it is if you happen to be looking at your more involved notes, you'll see that technically speaking, hydrogen carbonate is a special kind of acid, and it says that they're soluble, right? So treat all acids as soluble. H2CO3 further decomposes into carbon dioxide and water, which brings us up to a lot of things that we don't have to worry about. But for the most part, this is an aqueous solution. So that's how we have to attack every single one of these problems. We have to use the reaction template, which is double replacement reaction. And if you couldn't remember that, here it is on this back of your periodic table right here. There's your double replacement reaction. And then we just match stuff up with it and move it across to the other side. And then you check your charges, you apply your solubility rules, and all those things, and you can figure this out. So really, for number 14, potassium and nitrate came together, and silver and bromide came together. You got KNO3, which had to be aqueous because of rule 1 and rule 2. AgBr had to be a solid because of rule number 3. Number 15, sodium and chloride came together, and strontium and sulfate came together. So you got Na and Cl, and it was aqueous because of rule number 1 and rule number 3. Sr and SO4 was aqueous because of rule number 4. So that, so actually in reality that should, well, we'll talk about that in a minute. And then lithium and so for rule number 16, lithium and phosphate came together, and that was aqueous because of rule number 1, but also rule number 5. Calcium and acetate came together, and that one is also aqueous because of rule number 2. And then lastly, for number 17, aluminum and hydroxide came together, got AlOH3. Rule number 5 says it's a solid. Calcium and sulfate came together, you got CaSO4, and that one's aqueous because of rule number 4. Now, what I didn't include up here, which I probably should have, is what happens. So because a solid forms with MgPO4, I'm going to go steal this from up here to make my life a little bit quicker. Reaction occurs because solid forms, Control C, come back down. Okay, so because the solid forms here, the reaction occurs. Oops. The reaction occurs. Here I have a solid in this one, so that one is also going to be a reaction occurring. And then if I look down here at this one, there's no reaction occurs. So what I'm going to steal from up above is, I didn't do it. So I'm just going to write reaction does not occur because no solid forms. Okay, so that one I'm going to make. Consistency is really important to me. Okay, so that reaction doesn't occur because there's no solid forming. And then also with problem number 16 or question number 16, you should note that there's aqueous product and aqueous product, so the reaction does not occur there as well. But then lastly, yes, the last one does have a reaction that occurs in large part because of the solid forming of AlOH3. All right, the last thing that you had to do was you had to go ahead and just simply identify if these were aqueous products or solid products, and then you had to throw a little balancing in there. 18 was balanced 1, 1, 1, 1, not too bad. KNO3 is aqueous because of rule number 1 and number 2. AgCl is aqueous because of rule number 3. Number 19 was balanced 1, 1, 1, 2. PbCrO4 is a solid because of rule number 5, and KC2H3O2 is aqueous because of rule number 1 and or rule number 2. So at this point, I've gone through every single answer on this worksheet, and hopefully now you feel a little bit more confident with how these problems work.